Okay, hello. So I'd like to welcome you back to what hopefully is the start of us running these weekly video sessions again. And we're going to start with something that's a little bit different. It's, in a sense, a reaction to one of the questions that we encounter fairly often. So Heather and I, who give these videos, mostly work in compiled languages. So the entire point of a compiled language is the code that you write is transformed into the low-level instructions that the computer understands. And that produces extremely fast results. As fast as a computer can run something, potentially you can write code to make it run that fast. But it does come with some consequences, mostly that it means there is no way of executing new instructions, or at least no easy way of executing new instructions that you didn't write into the program when you compiled your code, when your own source code was transformed into those machine level instructions. Now, for people who come from an interpreted language background, something like Python or Perl or Lua or any language like that, this will feel very peculiar. And the reason, as I say, is quite simple. It's because when that compile step happens, your code gets transformed into the commands that the actual computer's CPU understands, and it can't do anything but what it was programmed to do. Whereas with an interpreter, the instructions are being run by this interpreter program, so you can always give it new instructions here and now. And so Python has its eval function, for example, that allows it to evaluate other Python expressions. Now, whether that's a good idea is a much more complicated question, but you can do it very easily. So one of the questions that does come up fairly often is, I've written something in C or C++ or Fortran or Rust or whatever. Is there any way of executing, having the user of my program specify some kind of an expression and having that be used in their program? And the answer is yes, basically, in three different ways. And I'm going to talk here about one of them, but I'll mention the other two first. So the first one, and in some senses the most difficult, is to break that assumption. So I said you can't have new code added because it's transformed by this compiler. And that's not true. There is nothing fundamental to the way computers work stopping you taking new code, compiling it, and putting it into the code that your program is executing. And there is one major library that does that kind of work, which is called libllvm. That would let you do that. It's not easy to use, but you can do that. There are also tricks to get around having to use something like LLVM, but doing the same sort of thing, but it's always a bit messy. Number two, and by far the most popular approach, is to embed an interpreted language inside your compiled program. And the most popular for this nowadays is probably either Python or Lua. Python, because so many people can program in Python, so if you put a Python interpreter in your code, potentially a lot of people can write this internal scripting language that you've now given your program. And Lua, because it is really well designed for embedding inside other programs. Python is really meant to be a standalone programming language. You can put it inside your program, but it's not easy and it's not particularly well suited for it. The third option is you can write your own. And it's not easy to write a really useful one. But a basic one is quite instructive. It lets you see what's happening here, and it lets you understand what's going on. And I'm now going to introduce a term that you may have heard before in a different context, which is that of a virtual machine. So virtual machines are something you may have come across, and the idea of a virtual machine is you can use it to run one operating system inside another operating system. So, you can be sat at a Windows machine and have a Linux computer in a box, or you can be sat at a Linux machine and have a Windows computer in a window on your desktop. And that's really useful. But before that use of the term virtual machine came along, there was another one. And the idea of that was it was something that modeled the way a computer's processor worked in software. So effectively, you would be creating a type of CPU, usually a very simple one, inside your computer that ran in software. And actually, this is how most of these interpreted languages work. They have something at their core that is basically a virtual CPU, a virtual computer. It is worth pointing out that a very special form of this is things that emulate specific physical CPUs that used to exist, and they are emulators, where you literally emulate another computer inside your computer, and there are ones for people to use old software and various things like that. We're not going to go anywhere like that sophisticated. We're going to talk about what is called a stack machine, which is a very simple form of virtual machine. Now, first of all, I am going to suggest that if you want to have maths done on a computer, which is what this is ultimately about, being able to input a mathematical expression, this thing can all be generalized to doing more complicated things than maths. That's how things like Python and Lua work, but we're just going to talk about maths here to keep this within the scope of a single reasonable length video. And I'm going to suggest that the way you've been writing your maths all these years is not very helpful if you want your computer to run them. So, first of all, here is how you would normally write a piece of maths. Now, this particular sort of thing often crops up as a puzzle. People will send them around to their friends on various forms of social media and the like, because what you have to remember to get the answer right here, they're usually more complicated than this, so it's something like this, is that you have to do this multiplication. I'm using an asterisk here for multiplication rather than an X symbol. Is that you have to do this first and then the addition afterwards, because there is the concept of precedence. And the way you actually do it is if you have a long list of these numbers combined with these mathematical operations, you have to hunt through, find the operators with the highest precedence and do this first. So here you take this 5 times 9, say, okay, 5 times 9 is 45, collapse that, and you now have 2 plus 45, which is 47. What you absolutely can't do is do the 2 plus 5 first and multiply it by 9, because that gives you an answer of 63, which is different. If you need it to happen in a different order, you use brackets. So if I wanted to do 2 plus 5 and multiply the result of that by 9, I'd put brackets around the 2 plus 5. Now, formally, this way of writing your maths is called infix notation, because the operator goes in between the things that it is operating on. So you have 2, a number, operator, plus 5, another number. And now there are 2 other forms of maths notation which are formally called prefix and postfix, where the operator goes before or after. And we're interested in the one that's technically called postfix, but is actually more commonly called reverse Polish notation. So the thing with reverse Polish notation, as I'll show on the next slide, is you don't have to do this hunting through to find operator precedence. You just go from left to right and you operate, number by number, operator by operator, going from left to right. There is also just Polish notation, which is the prefix version. That is, as far as I know, much less common than reverse Polish notation, the postfix form. So just to make this absolutely clear, if you had something simple like 1 plus 1, in reverse Polish notation it will become 1, 1 plus. And I'll go through a few more examples. So we'll take my example from the previous slide, 2 plus 5 times 9 in infix. Now, because there are no brackets in that, I do the multiplication first. So that becomes 5, 9, multiply, 2 plus. Okay. And I can just do that from left to right, because basically the way you read it, in a sense, is just as I showed with the infix. You do this bit first, you do 5, 9, multiply, and that gives you an answer, and then you take 2 as another input and do the addition. If, on the other hand, I had brackets in there, so I wanted to do brackets 2 plus 5, close brackets, times 9, that would become 2, 5 plus 9 multiply. Again, I can just go through that from left to right, and I'll get the right answer. And you can do this even with things that are functions with their own brackets in Infix. So, for example, sine 2 times pi, which is 0, by the way, because that will come back, becomes 2 pi multiply, because you do the inner bit first, sine. And so that is just a different way of writing your maths. The reason that this is potentially important is because this actually maps very, very neatly onto a data structure that are quite natural for computers called stacks. Now, we have a blog post from a few years back on stacks, and I'll put the link to that in the description of this video if you don't know what they are, but we'll go through the basic idea. And just something to sort of bear in mind, a stack basically works sort of like it's something you might have seen in TV shows, because it used to be something that was used as a sign of being in a newspaper room, because they really were used in newspapers. It was just a spike, and something would come in and it would just get stuck on the spike, and you put new things on at the top, and things could only come off in the reverse order to the way you put them on. So, think of it like that. Think of it like a train siding. We'll actually come back to that later, because, if you put a load of train cars on a siding, you can only pull them off the siding in the reverse order that you put them on. But to evaluate this maths, you can have this idea of what is called a stack machine. Now, stack machines are things that do exist. There are physical hardware stack machines, but we won't be talking about them. We're going to be talking about a very simple software stack machine. So the idea of how they work is that you have a list of instruction values that either push a value onto a stack or pop them off the stack to use them. So pushing is putting something on, popping is taking them off. That is not my terminology. That's really standard. That's what people who work with stacks call this. So, for example, if you had a number 1, all that would do is a number 1, the instruction is put a 1 on, so you put a 1 on the stack. Then let's say you have another instruction of put a 2 on a stack, and then you would have a block that is plus, and that'll go, I need 2 numbers, so I'll pop 2 values off the stack, add them together, and push the result back onto the stack. And because of this behavior where you push the result of an operation back onto the stack, subsequent operations can make use of them. So this can seem a little bit bizarre, but let's actually sort of see it graphically, because that makes it fairly obvious. So here is that 2 pi, the sine 2 pi thing that I had earlier, written in reverse Polish notation, postfix notation. And here is my set of instructions, my list of instructions, and I'm going to be working from the bottom up here. So, first of all, I encounter a 2. 2 simply puts 2 on the result stack. I now encounter pi. Well, pi is a named constant, but it doesn't take any values. Pi is just pi. It's 3.14159, etc. So I just push that onto the result stack. I now encounter the multiply operator, and that multiply operator consumes 2 values from the result stack, this 2 and this 3.14, etc., etc., multiplies them together and pushes the answer onto the result stack here, and you get 6.28. The sine function takes only a single value and pushes the result of that value onto the stack. Well, sine of 2 pi is 0, so it will pull off this 6.28, take the sine of it, get back 0, push that on, and then to get the result of that calculation, I just look at whatever's left on this result stack. I have done maths myself in terms of this set of instructions. And these are not CPU instructions, these are instructions to my program. So at this point, I shall break away from that, And I will actually show that implementing that is not very difficult. I'm going to be doing this in C++ because in C++ there are some very helpful elements that mean I don't have to write my own data structures the way I would in C or Fortran. So C++, definitely the easiest language for doing this, and we'll make this code available on our GitHub page, and I'll put a link to that in the video description as well. So I'm going to implement my actual stack machine as a header, and only as a header, because it's really very short. I'm going to call it just call it stack.h. So first of all, I just put in my include guards. If you're not a C programmer or C++ programmer, this will look a bit weird, but it has to be there. And now we start writing actual code. So first of all, I need some of the built-in data structures. So I'm going to need a vector, which is a list of those instructions. I'm going to need my stack, because I've got a stack. And I'm also going to need a header called functional. Now, functional explains some of how I'm going to do this. So the idea of functional is it contains something which is called a standard function, std : function, and that is a way of storing a function so I can call it later. If you're a Fortran programmer, it's a procedure pointer. If you're a C programmer, it's a function pointer. And if you come from Python, it's like assigning a function to a variable by name. There's actually a lot of fundamental differences compared to Python there, but never mind too much. So the first thing I'm going to do is I'm going to write myself a wrapper around the built-in C++ stack. Now, the C++ stack works very well, but it has one rather annoying feature, which I'll explain as I get to it. So I'm going to call it my output stack. And it's going to have one private member, which is a stack of floating point values, which I'm just going to call _stack. Okay. Now, we now come to the public bit. So I'm going to implement my push method, which takes a value. And that really is a very simple wrapper to the underlying stack, which has a push. Now, pop is where it gets a bit, where you can see why I need this wrapper, because the built-in stack in C++, for very good reasons, doesn't actually allow you to pop a value off and return the value at once. If you pop a value, it just throws it away and you never see it again. So what I do is I get the top element of my stack, which gives me the value of it but doesn't take it off the stack, and I'm then going to pop it. So at this point, I now have a very thin wrapper around my stack that just makes everything else that bit more elegant. So not very interesting. I'm now going to write my I'm going to call it interpreter. Okay. Now, inside this, I'm going to have a list of functions. Those functions are going to be the functions that actually do the job. So I'm going to define a vector, which is a list in C++, a nice easy to use list of these standard function objects, and the functions that I'm going to be storing are all going to have the same signature, which is they're going to return void, and they're going to take one of my output stacks, a reference thereto, as a parameter. Okay. And I'm going to call that iList. It's my list of instructions. And I'm also going to have inside just an integer, which I'm going to call stack point. Now, if you were building a real one of these, there's a lot of these design decisions you would take differently. This is designed to be compact, quick to program, and fairly clear for what it's doing. But the stack point is which of these instructions we are currently executing, basically. Okay, I'm going to create a couple of public methods for this as well. And the first one I'm going to create is going to be to add a instruction, and it's going to take one of these functions, which, dear me, I used the wrong type of bracket in that. So I'll just copy this definition, and there we go. I'm going to call that op because it is an operation, and all that does is it pushes that operation into my list of instructions. And I'm going to write myself something for convenience. So basically what this is doing is it is allowing me to pass a function in. It will store that function in the list of functions that it's going to execute. Now, quite a lot of those functions are going to be literally just push a value onto the stack. So, if I want to do 1 plus 1, I would have to do 1, 1, plus. Plus is the only one that does anything interesting. Because basically each of these functions is going to be called, and they're going to push their value onto the output stack or pop values off the output stack so they can get their parameters. So there's going to be a lot of things that really do literally just push a single value onto the stack for these numbers. So I will also write myself a convenience version of add instruction, which just takes a float, and that's going to use a lambda capturing this value. A lambda is a kind of inline defined function. They're actually more than that, but if you're not familiar with them, don't worry about them. It's a way of just quickly defining a function that I can store and use here. So I'm now going to take that output stack reference, and my function, when it executes, is going to take that output stack and it's going to push on the value that I've just given it. And there we go. That has created the two versions. So I can, with this function, I can add any instruction that I like. And with this function, I can quickly and easily, except I haven't done that right. Oh, yes, of course. So what I have to do here is I have to also made a couple of mistakes actually. That is not list, that is ilist. And I have to push that function on to ilist as well. So there we go. So those are the two things. Now all that I have to do is write the thing that actually executes that. And you'd think that's in some way clever, but it really isn't. It's going to be something that is a float, and oh dear me, returns a single float, and I'm just going to call it exec, and it is not going to take any parameters. Now I'm now going to create an output stack, which I'm just going to call S for simplicity. I'm going to set that stack point. No, I'm going to do this a simple way. So I'm just going to go for int I. I can do it this way. Auto function ilist. Get references to them because there's no reason not to. And then for that function, I will call. Right. So this can look a bit peculiar, but what I'm doing is I'm creating one of my output stacks here so that I can evaluate values on it. And then this is just looping through all of the instructions that I have in this vector, all of the ones I've previously added, and it gets out fn, each function in turn, and calls it with this output stack that I've just created. The last thing I need to do then is I need to do return s.pop. So as I showed at the end, I then just pop off the final answer. So on its own, that doesn't look like much, but that is a fully functioning stack-based calculator, essentially. However, at the moment, I haven't actually given it any instructions to operate on at all. So that's where the next bit comes in. So I'm going to call this calc.cpp, and I am going to include stack.h. Is that what I called it? Yes, stack.h. And I'm also going to include IO stream so that I can print my results. Okay. Now, I am going to create my main function, which is, of course, my entry point. And I'm going to take in, usually when I write these examples, you see I don't bother with these parameters here because these are used for command line arguments in C and C++. But here, I'm going to make use of those command line arguments because I'm going to write a calculator where I can put in this reverse Polish notation stuff at the command line and get out an answer. So I'm actually going to include maths, but I won't do that straight away. So I'm going to do a little bit of a trick here again. So I'm going to use another C++ data structure, this time one called the unordered map. Actually, I'm just going to use a normal map, no point getting clever here. So the idea of a map is I can map between certain keys and certain values. And in this case, I'm going to map between a string and a function. So I'm going to just create some my map first. So my map is going to be a map between, oh dear, I forgot I need string as a header as well. Okay, map between a string and another one of those standard functions, which look exactly like the other ones. So it's void output stack ampersand os. Okay. And I'm going to call it my function map. And I'm now going to do function map of plus is going to be another one of those lambdas, but this time it doesn't need to capture anything. And okay, takes a while to write these the first time, but after that it's a lot quicker because I can just copy and paste. So I'm just going to do os.push, so push my answer onto the output stack, os.pop, get the first parameter, plus os.pop. Okay, and there we go. So that is now mapped between the concept of plus, the symbol, and this operation of taking off two values, adding them together, and putting the result back onto the stack. I'll now do the same. I'll actually copy it as I said. Okay, for minus. So minus, the important thing to note is, of course, the things go on backwards onto the stack. So here you might think that I could just switch this plus here for a minus, but that wouldn't be right. That would be doing the minus backwards. So instead of getting a minus b, I'd have b minus a. So the easiest way of doing that is I just put a minus symbol there. So that's minus b plus a, which is the same as a minus b. Okay, I'll then do another one of these map things for multiply, which now really is as simple as doing that times that. And unfortunately, I couldn't think of any clever way when I was looking at this for doing divide. So I will in here create two floats. I'll first of all create the denominator, which I pop off, and then the numerator, and then I will push on the result of the numerator divide by the denominator. And I should change that from star to that. Now, star, I put star here. I should not have put star here. Star will not work properly. Because I'm doing this from the command line, star gets intercepted by my command line interpreter and expanded into the list of all files in the directory for me. So I can't do that. I will use X instead. Okay, so that's basically it. I can now do the 4 basic operations. So I will now create, what did I call it? Interpreter, that's what I called it. I will now create my interpreter, and I will loop through all of my command line parameters. Now, if you are a C programmer, you will wonder why I am starting from 1. Well, if you're a C programmer who doesn't know about how command line arguments work, it's because the 0th command line argument, the actual first one, is the name of the program that's being executed. So I'm only interested in ones after that. Okay. So in here, I'm going to use the S2F command to try and convert the input into a number. Okay. So I'll call it val S2F argvi. So I'm trying to convert my string command line argument to a number. If it succeeds, then I can use that handy overload I created to just push that value onto the instruction. I didn't call it push, I called it add instruction. So technically, the instruction list is a stack as well, which is so some of my earlier versions of this said had pop and push for those as well, but add instruction. Okay, if I don't successfully convert it to a floating point, then it's an operator. So what I will do instead is I will do I.add instruction of that function map of my argument instead. And that then builds my instruction stack. So all I should have to do is do standard cout to print exec and a new line afterwards. Now, we will see whether this actually works straight up. Yes, of course, not math, C math. Okay, so I have made a mistake. I made a warning. Oh, okay, so that's actually very silly. So first of all, yeah. Here in my implementation of this, you may well have spotted it before I did. I must, of course, return that f that I captured. And here I've just shadowed my own variable name. So I used I for my loop variable here. I will just switch that to be called j. Realistically, I should have picked much more sensible names for everything, but I didn't. Okay, and that now compiles. So now if I run a.out on its own, I get a seg fault. However, if I put on numbers, if I just put on 1 and 2, then all I get out is 2, because that's the last thing that got put on the stack. But the magic happens if I do 1, 2, plus. I get the answer 3. If I do 1, 2 plus 6x, I should get 1 plus 2, which is 3, times 6, which is 18, and I do. So there we go. In that very short set of expressions, I have successfully written a calculator, and I really can, if I give my problem in reverse Polish notation, anything that involves just addition, multiplication, subtraction, and division, it will work, and I can put in non-integer numbers if I want. There we go, 6.6, and it will work. And just to demonstrate that I can actually solve that problem that I did earlier, I will just put in here quickly pi, and now I want that, which is os.push 3.14159. In reality, I should, of course, pick a proper value for pi, but that'll do. And I'll put in sine in much the same way. And now I will need to push on sine of the popped value. So that should now work. I can recompile my program. Oh yes, forgotten I semicoloned on the end of those lines. Yeah, messed that up a bit. Okay, so if I now do a.out and I do 2 pi times sine, I get a number that's almost 0. It would be a lot closer to 0 if I put in a proper value for pi. And if I do, instead of 2 pi, pi by 2, I get 0.6, which I think is a correct value for sine pi by 2. I can never remember. No, that's 2 divided by pi, of course. That's why that won't work. Pi 2 divide, and I get 1. There we go. Should have remembered that. Anyway, so that is now working. It has a lot of things you'd want. It has functions, it has named constants, and you can extend this a very long way if you want to. The main thing that limits its use at the moment is the fact that humans don't really like reverse Polish notation. Now, I will say that is quite a substantial simplification there, because of the fact that Hewlett-Packard did actually have a set of very successful reverse Polish notation calculators that people loved and were very upset when they stopped making. But there is a way of going from normal infix maths to this form that computers like evaluating. And you only have to do that once, and then you can evaluate it as many times as you want. Now, that standard algorithm is called Dijkstra's shunting yard algorithm. Edgar Dijkstra, a very prolific computer scientist, had lots of algorithms. Quite a few of them are named after him. This one is the shunting yard algorithm. So the idea of it is that you sort of want to turn your normal maths inside out. And as it turns out, you can do this with stacks again. What you have is one stack that contains the output and an intermediate stack that holds functions and operators until you've put their operands in the output stack. Now, the real algorithm is actually quite complicated and quite messy because you have to deal with that operator precedence, you have to deal with operator associativity, and various things like that. But you can see how it works fairly simply for simple cases. So let's take my example again, but written now in infix. So I have sine 2 times pi, and I've coloured all the bits differently. So you go through, and the first thing you encounter is sine. So sine is a function, so it goes on that intermediate stack here, because it can't go on the output stack, it doesn't have any operands. 2 is just a number, it doesn't take any operands, it's just a number, so it goes straight on the output stack. Star, multiply here, again, function, goes on this intermediate stack. Pi, it's a named constant, but it doesn't matter, you don't need any values, so it goes straight onto this output stack. And then you encounter this final closing bracket, and that's a trigger to just take all of these things here off the intermediate stack and put them on the output stack. And you can see that what you get is 2 pi star times sine, which is exactly what I said earlier was the reverse Polish notation. And that's basically the end of this. Now, I will say very definitely, you probably do not want to implement things like this yourself for working code. They're not likely to go wrong. As you've seen, they're pretty simple. You can write versions that are a bit less simple and have a bit more power. You can write versions that are a bit faster than this. That standard function thing that I used is not quick. But as a general rule, you don't want to write things like this yourself, if only because they are really quite limited. The interesting thing comes if I changed how those functions work. So those functions just take the output stack. All they can do is they can put values onto the output stack, they can take values off the output stack. But imagine now that you have something that's handed not just the output stack, but the input stack as well. At this point, it can theoretically modify its own code. It can certainly change which element of the code it's running on. That's why there was that stack point thing variable that I created, and I never actually used in the end. It just looped straight through from start to end. But in a more general version of this, you use that stack point variable, and it can be modified by these instructions as they execute. And at that point, your your stack machine can actually be increased to being a true computer. You can implement loops, you can implement conditional branches, you can do a lot more sophisticated things than you can with just this simple approach, although you can actually get a long way with this simple approach. The main reason that we thought this perhaps something that's useful to see is, well, A, it's potentially quite interesting, particularly to see just how short the code necessary to do it is, but equally because it takes some of the mystery out of trying to write, of using things like a Lua interpreter or a Python interpreter. They're not working exactly like this. This stack machine is a very specific way of doing this kind of calculation, but there'll be something a little bit like it behind the scenes. You have state, you have things that consume pre-existing state items and return new state items. You have other things that we don't have here, like ways of storing to bits of memory and retrieving from bits of memory. But this is very much the beginnings of how you write your own interpreter. And as you can see, it's really not actually that complicated. So I will finish there, and we will, I hope, be back next week with another video.